Hi and welcome to the next talk at Meeting C++ 2025. 3 speakers, a little bit different topic, and I'm looking forward to see the insights into entity component systems. Please take it away.
Okay, thank you very much. My name is Helmut Hlavacs. I'm professor for computer science at the University of Vienna, and today we will present together with my students Isabella Hölzl and Marlene Kasper. We will present insights into entity component systems. So who are we? I'm professor for computer science. I've been into C++ since the early 1990s. My research focus is on video game technologies and game applications, and I've been teaching game-related technologies like AI, physics, data structures, the Vulkan API, and so on for the last decades. And I'm also author and founder of a lot of projects on my GitHub. One of them is the Vienna Entity Component System, VECS. Another one is a Vulkan-based game engine, a physics engine, and so on. So we're really into creating our own software. We are C++ focused. And the reason for creating this software is to learn about the technologies for teaching, so we can hand out theses for our students, and also to use them as basis for our courses. However, it is not intended as production code. Now, if you look at modern video games, they have a couple of requirements. So usually you have many entities that have to be simulated and rendered. Very often, even thousands, hundreds of thousands entities, can be bullets and particles and so on. And many of them have runtime behavior, so you can use AI, you can use physics simulation. So in order to maintain some kind of a frame rate, you have to be very efficient about what you're doing. So you have to be memory efficient, you have to be cache friendly in what you're doing in order to have a good performance coming out of that. Parallel processing, multi-threading, of course, is a big issue nowadays. And you have also different parts of the game engine systems that have complex interactions and that have to interact with each other. Now, if you look at entities that you are simulating in a modern computer game, we can come up with an example and demonstrate why object-oriented design is maybe not always a good idea. So for instance, if we have a very general game object class, and then we want to derive more precise classes that focus on specific behaviors. So here we can come up with like an item class, a character class, an environment class, and then from the character we can even more specify, be more focused. Maybe it could be the player, him or herself, could be an enemy, derived an enemy class, a non-player character, sidekick, whatever. And then if you look at an enemy, enemies can have different behaviors and different things they can do. So for instance, they can fly. It can be a flying enemy, it can be a shooting enemy, it can be an enemy running on the ground, and so on. The problems arrive when you want to combine these things. So you could have a flying shooting enemy. Then you would have to derive from both of these classes. You could have a flying shooting spellcasting enemy even. Using traditional object-oriented design here leads us to this problematic class hierarchy. We have a combinatorial explosion of different properties that we would like to inherit. Maybe we would even be forced to duplicate code or to bubble up functionality to a higher class. This is not what we actually want, and this makes object-oriented design undesirable. Moreover, if we, for instance, have a situation like this where we put all of our game objects into a big array and then have some kind of virtual function like update or tick or whatever. So we put all of them into this big array of a pointer, and then we run through the array and call tick or update or whatnot. Then we would actually have to call very different virtual functions and virtual tables. So we would actually be forced to jump around in main memory. So we're using virtual functions in a bad way. So this is not cache friendly. And every new behavior would require a new class. So object-oriented design in this sense is quite problematic. So how can we solve that? Now, we have seen that our entities have different aspects or components. And one way to solve that is actually to view entities as combinations of components. So for instance, a flying enemy would have components. It would be a game object, so it would have a component game object. So all the data would be in this object, or in this component. It would be a character, an enemy, and it would be able to fly. So we can compose now this entity of these components. And depending on the enemy or on the entity type, we can compose entities using different combinations of components. So a shooting enemy, for instance, would be a game object, would have the component character, would have the component enemy and the component shooting. And now we don't suffer again from this inheritance problem and maybe the diamond of death where we have to derive from a multitude of classes. So this comprises an entity component system. An entity component system is based on 3 pillars: the entities themselves. So conceptually, an entity is like an unordered set of anything. Now, of course, that set of stat any doesn't work because there is no less operator. You cannot order that, but you could put it in the wrapper and define some less operator here. But this is more or less the idea of what an entity is. It's an unordered set of anything that you can put into this entity. Now, an entity is composed of components, and components are supposed to be pure data. So it's not allowed or wishful to attach some behavior to that. So components just data, maybe plain old data, just a plain old data structure. So for instance, this could be the position of the entity, its velocity, its inertia tensor, its or other aspects for rendering, for instance, textures and other buffer types. And finally, you need game logic. So the functionality that is working on single components or groups of components. That's called systems. So you will have lots of systems. They can be as simple as being just a function. And a system is now tasked to cover a very specific functionality, like making an update for the physics engine or doing some game AI stuff. And then it will select specific entities that have specific components, run through them, and call update and do their magic. So we favor composition over inheritance. So in order to to program an ECS is more or less a data structure, a container. We can put stuff into it, change it, or erase it. So this would be typical ECS operations. We can create new entities. For each entity, we can add components or erase components. So that is typically something very dynamic. We can change entities by just putting more components to this entity. We can read or change component values. That is important to make an update to change that. We can erase whole entities. And finally, very important, we can iterate over entity groups. And here we can select entities that have specific component types like position and velocity, but also we can apply labels. So we can use labels to further be able to group more specifically. So for instance, an AI system might iterate over all entities that have a position and a velocity, and additionally have the label in being intelligent, but this specific AI system is not interested in anything that's very heavy. Maybe it's some lightweight entities. So you only select entities that have these component types, have the tag intelligence, but do not have another tag. So you can create very flexibly groups, in groups and out groups. So in my own entity component system, this is a sample code where you can actually create stuff. So the basic container would be this structure, a registry, and we use handles actually to find stuff, to find entities. So for instance, we can ask, does the handle point to some entity or has it never been initialized? Then we can insert an entity and put into, when we insert it, we automatically can put stuff into it, like a string here, for instance. When we insert an entity into the container, we get a handle that identifies the entity. And then we can also test, for instance, whether this handle points to an existing entity. It might not exist anymore simply because you might add entities, but you can also erase entities. So after having been erased, the entity no longer exists. We can insert more stuff. For instance, here I would insert an entity that has components, an integer and a floating point. And then we can ask, does this entity have a component integer? And here we use the type of the component as an ID for the component itself. We can also call get, and then we would get the value, so we get a copy of the value, and we can later see also that we can also get references to these components. Finally, we can erase an entity, call erase, give it a handle, and it no longer exists. Now, because we use types of components in order to identify a component uniquely, we cannot insert components of the same type twice. So I cannot insert, for instance, an integer and another integer. That doesn't work. So we have to make sure that whatever we insert, that cannot exist, so that we cannot exist duplicate types. So if we want to insert duplicate types, we have to put them into wrappers. So here we would define a height struct and a weight struct and put in an integer in both things. But of course, they have different types, so we can happily insert them all together for the same entity. And also we have attached also the semantic of what we need, what we mean with this component. Now, components are unordered. So as I said, types are unique. We have to enforce that. We might either use wrappers, or you can use also your own strong type if you want. I defined my own strong type. It's a strong type that is more than just a wrapper. It uses also some convenience functions for bit manipulations. And I also use a type counter as a phantom type. I lifted it from this talk here, and it will allow me to create different types without a phantom type. Doing that would result actually in the same type because it's just an alias. Using is just an alias. But if I insert my own phantom type counter, then both using structures will result in very different types. And then we can insert them and into the entity component system safely. I also said that one main application is to actually iterate over groups of entities. And here is an example. So for instance, this might be an update function implementing a physics step. In this case, it's a symplectic Euler step, like for the differential equations to move entities forward. And what we do here is we get a view. And the view simply is a container defining specific groups of entities that have all of these components. So in this case, I want a view over all entities that have a handle, a position, a velocity, and an acceleration. Also, we see that here we have a reference. That means that the view will get me the value of the handle. Well, you can't get a reference to a handle because that's fixed. You can change that. But then we get references to position, velocity, and acceleration is just a value. So once we have the view, we can put it into a range-based for loop. Here with structured binding. And this is handled automatically. So we loop over all entities that have these types as components, and position and velocity are now references. So we can write over them, whereas acceleration is just a copy of the value. Now, in reality, these are not real C++ references. There are some problems involved. I will come to them later. This is just a reference object that actually tracks entities because entities can be moved, as we will see. So before going into details about performance, thinking about using ECS in your project, you have several options, and these are the steps that I would recommend. If you want to use an ECS in your project, by all means, use one that is mature and highly performant. And there are a couple of standard ECS that you can easily get, like Entity or Flex or Pico, and they're highly optimized. There's a lot of effort in that, and probably the best choice. You can also create one with a large language model. That's surprisingly easy. You can also create one yourself, and I would recommend first to create a simple one and then focus on performance. And only if you really need high performance and especially API and so on, then you can actually invest more into your ECS that you really want to use in your project. Now, speaking of large language models creating an ECS, I typed this into Claude. Claude created a simple C++ ECS with templates, and out comes this source code. And that's perfectly valid, super simple ECS. It uses this kind of data structure. It's a very good idea actually to use that. So here we have entities are just size t, so this is just an integer. So the handle here is just an integer that is counted up. Whenever you get a new entity, you just increase it by 1. And inside the entity, you have a map that maps the handle to a specific data type. And whenever you want to have access, you call get storage for a specific data type, and you get this storage back. So that's a reference to the storage back. So that's actually a pretty intelligent solution. There is no need to explicitly create that in the heap. This is automatically created by the compiler. And again, we have the typical operations. We create entities, we add components, we get components, we remove entities. And we get a view, which is simply the data structure itself. Now, thinking about efficiency, of course, we can now organize our data in very different ways. And the way we organize our data, the data layout, has a very big influence on performance. I will show a couple of measurements later on. And of course, you have to ask yourself, is performance important in my project? And if it is not, by all means, I would choose either an existing LLM or really create a simple one, like using an LLM. However, if it is important, there is, of course, a difference between latency and throughput. So latency means anything where you put in stuff or search specific entities, whereas throughput would be to iterate over large arrays of data of components, and how you can do that efficiently. Both might be important. Latency is directly related to how you organize your data structure. Is it a tree? Is it an array? And throughput is more or less the question, are you doing this in a cache efficient way? Now we have all of these standard template library containers, and of course there are more, like flat maps. So basically a map is simply a tree, and all of these nodes are somewhere on the heap, so that is allocated from the heap. So whenever we go through all of the nodes, I jump to another memory address, and therefore I'm very likely to have a cache miss. So right off the bat, organizing your data in this way is not very cache efficient, and you will suffer a performance penalty for that. If you have an unordered map, situation is slightly different. You have this kind of data layout. If you have all the hashes, and you go to the hash of your handle, and then you have a list kind of structure. And sometimes you have more objects in this list. Sometimes you have only one member of this list, depending on how many cache collisions you have. If you go down this list, you will have cache misses. Now, this is probably the most efficient way to store data and iterate over it, putting it into an array. So it could be a vector, for instance. And if you go from top to bottom, and if you have very regular access pattern, of course, this is highly cache efficient. You have cache prefetch. So the memory logic will prefetch data because it thinks you will need them in the future. So this is highly efficient. So cache efficiency is really, it really depends on how the data is stored. Is it stored contiguously in dense arrays? Then you have very high efficiency. And that is very good for systems. So systems really run through all of the data, or large parts of the data, every loop. So they do this every frame, every single frame, 60 times a second or even 100 times a second. Many systems will go through all of your data in some way. So that for video games, that is really important to have that. So high CPU cache efficiency is important for computer games. And in order to demonstrate this, I have run some experiments. These are two arrays. In one array, so here is the size of the array on the x-axis, on the y-axis, the time. It's the time in microseconds. I need to read all of them. So in the dashed line, what I do is I go from top to bottom in a cache optimal way, and I see that it's very quick. And in the solid line, I actually jump around in a random fashion. Eventually, I will read all of them, but the ordering is totally random. And we see that I have a big performance hit already. So this is just one component that I go through, either linearly, that is very efficient, or randomly, I have a lot of performance hits. Now, in reality, you will probably not store all the components in a contiguous array going from top to bottom, because you might have problems allocating that much memory. So probably you will allocate segments and then use another data structure to point to the segments. And if the size of the segments in number of components is a power of 2, then you can very efficiently go from an index, find the right segment, and then find the right component in the segment. And that way, that of course, you can grow this data structure infinitely as long as you have mean memory. And also very well, you can put this into very efficient memory tiling structures. And when you grow the data structure, it is not reallocated, because when you grow a vector, the vector is actually reallocated, and if you have any reference or pointer to any of these, they go out of their context, so they're actually stale. So having this kind of your own vector structure is highly positive, and should use that. Now, in reality, you really want to iterate over many different components in one go. So you want to go over all game objects and all characters, for instance. And in order to do that, you can, for instance, organize all of your components in this array, and here, and all of the character components in this array. And then, if you want to run through all of the entities that have game object and character, for instance, what you can do is you run through this array from top to bottom, and then you see, this is the game object component of the first entity. The first entity has handle 3, and then hopefully you can use this handle to find the character component in the other vector. So that means that for the first component, you have cache optimal iteration, but then you access for every other component, you will have cache hits, because you will access main memory in a random fashion. That's quite a problem, actually. So let's see how that looks like in our performance view. That here still, the red lines are still the same, but now we see how long it takes to access actually not only one component, but 4, 6, 8, or 10 components. And the data is organized in that this is the time you take for the first component. So the first component access is always cache optimal, and then you have these random accesses through the other components, and you can see what the performance penalty of that is actually. Looking at this kind of matrix, we can see different types of organizations, different operations. You want to have insert, lookup, arrays, iterate over one component, or iterate over n components. And we can see that using standard data structures is not always a good choice. We can use unordered maps. On access, they are pretty good, but they can be very bad also. A lot of bad things happen if you actually iterate over n components at the same time. And here on the right side, we see actually something that looks very promising, and that's using slot maps and dense arrays. And finally, using slot maps and archetypes seems to be like the sweet spot. This is where we want to be. So what's a slot map? A slot map is a map that points to components in this case. And the way that you access any slot in the slot map is through a handle. Now we've seen handles, they can be as simple as an integer, but in this case, we actually split the handles, all the bits we have, like 32 bits or 64 bits, we partition the bits into two fields. They can be, each of them can be 32 bits, or you can shift that a little bit. So we have two fields. We have an index and we have a generation counter or version. So if you have a handle like 09, the first component would be directly the index into the slot map. And that means we have 01 access. If I know my handle, if I have my handle, I want to access the component, some component that belongs to this entity, I have a 01 order 1 access cost to do that. So this is directly my index. I go there, and then I have another index coming up saying, okay, what you're looking for is actually at position 2, at index 2 in this component table. So we have two lookups, but in 01 time. So that's very good. So what's the second operation? So as I said, what you can do with entities and components, you can add them, you can erase them even. So you can erase entities. And when you erase an entity, you still have a handle pointing to an entity that no longer exists. If that would be a pointer, your game crashes. You don't want that. So what you can do is you can use some part of the handle to make sure that whatever your handle points to still exists. And that's the idea of the version or generation counter. So whenever you bump out an entity, you simply increase the version number in the slot map. And whenever you want to access wherever this points to, you go to the index 0 in this case, and then you compare the version numbers. And if the version numbers are the same, then this means that this handle points to an existing entity and everything is fine, we can have access. But if the version numbers are different, then we know that the entity no longer exists, and the handle actually points to something that's no longer there. So we can't do that. It might result in a runtime error. Now, a slot map usually is a data structure that can grow and grow. Ideally, it would not shrink. It can shrink, of course. If it shrinks, then many handles are kind of unusable. You shouldn't use them anymore. If it doesn't shrink, then this mechanism of making sure that the entities still exist works very well. So what's the next step? So what's the best organization? So putting stuff into groups means I really want to iterate over groups of entities, and all of my iterations should be cache efficient. And the idea to do that is called an archetype. So an archetype is a data structure that holds entities that have the same component types and maybe also the same tags, depending on how you organize that. So in this case, I would have archetypes of entities that have the same components. Here we have also archetypes having all of the entities having different components and so on. So if, for instance, I have an entity here and I want to add another component, I have to move this entity away from this archetype, move it to this one archetype, move all the components here, and then add the new data. So changing components in this case sadly means that you have to move data, and that's some kind of overhead. However, what you gain is a very high cache efficiency. So here in this case, again, it's the same situation. We have seen the solid lines being going through the first component cache optimally, and then through the other components in a random fashion. And now we go through all of the components at once, and we see that again, our factor that we gain here is like a factor of 10, 1 order of magnitude. We are faster for that. So the consequences are adding and erasing components or tags and moves components to another archetypes. It's not advisable to actually use C++ references for that, because if you move entities and we have a reference to a component that has been moved, that can crash my system. So what I do in my ECS is actually to return a reference object that points to the slot map and not to the component itself. Also, when you move or delete entity or components while you're iterating over them, that means that you would have a gap, and you close the gap by copying the last entity over the gap. And that's, of course, not a good idea. When you're iterating over something and you erase it, then you would copy the last entity into the gap. And when you continue iterating, you will never see the last entity because it has been moved into the gap. So you have to really take care of things like that when you use archetypes. But otherwise, for games, this is kind of a highly desirable. And so now this is how my implementation looks like. So inserting something, it doesn't look like very much code, but of course you want to create stuff in the slot map. You want to create an archetype, and then you put the stuff into the archetype. That's more or less what's happening here when you do that. So, and with this, I will now pass on my talk to Isabella Hölzl, who will continue.
So, thank you very much, Professor Hlavacs. I will show you the topic I had for my bachelor thesis. What we have seen so far was sequential. So my task was to parallelize the Vienna Entity Component System. And I wanted to keep it simple, so I did it by implementing a manager class as a proxy. And it basically has a shared pointer to the registry as well as to the thread pool. And the thread pool is implemented as an interface, so we can easily switch it out if we want another implementation. The specialized functions I implemented to use multiple threads is, for one, the for each view. It basically operates like the get view we seen earlier, but this time you can also insert a function as a parameter, which then iterates over all the entities and applies the changes to the components. Second one is the insert bulk. This one is for inserting a number of different entities, but with the same set of components, which are initialized with their default values. And erasing entities in bulk takes a simple vector of the handles and then deletes all of them from the registry. So to avoid any race conditions, I used 2 different locks and 3 mutexes. So for any reading access, I used the shared lock. And for the writing access, I used the scope lock, which already comes with a implemented lock guard to avoid any deadlocks. And the registry has to be locked, for example, when we clear all the data from the registry, or as of now, still, if we want to insert an entity. The slot map has to be locked whenever an entity is erased, because this can, as we have already heard, can lead to any of the slots changing. So we wouldn't have access if we try to access them. The remaining functions are locked with their archetype, because when we, for example, erase a component, it can lead to change of the entity from one archetype to another. So in this case, we would lock the archetype it is currently in, as well as the other one it will change into. Now we have seen the parallel solution, but how does it actually scale? I have used the benchmark framework from Ableimer on GitHub. It uses 6 different components as well as 7 systems. Systems are, as we recall, just simple functions that operate on entities with specific components and change their data. So one of the benchmarks I used was updating. It simply iterates over a number of entities, uses all components and all systems. On the y-axis, we have the time cost per entity, and on the x-axis, we have the number of entities we iterate over. For the smaller numbers of entities, we group these to better visualize it. And the dark green bar symbolizes the sequential version of VECS, while the light green bar is the parallel solution. As we can see, with not many entities, like 8 to 128, we have a slight overhead, but this gets immensely better when we have more entities and up to 50% of speed up. While, for example, with another benchmark where we just iterate over entities without changing any of the data, we can have up to 30% of speed up. Since my main goal was to implement multi-threading, I didn't really focus too much on performance. So there are still some possibilities for future optimizations. For example, one which would be a little more effort would be implementing lockless scheduling inspired by the work contracts, which is a talk Michael A. Nescalco held at the CPPCon 2024. Or another possibility would be to move the thread pool deeper into the registry to improve the locking granularity. One other possibility is an archetype graph. So this is used by Sander Mertens already in his entity component system Flex. This would mean that we start whenever we have a new archetype, we insert that into the graph, and with time, we will have a graph that helps immensely with the lookup time, because whenever we want all the entities with position and velocity, we just return this with all its children. And another point would be to implement more bulk functions. For example, the bulk insertion for the components with not default initialized parameter components, but with values we give to the system. And for the erasure, a possibility would be to say that we want all entities with position and velocity to be deleted. So we just give the type into the function to then be deleted. And this concludes my part, and I will give the mic on to my colleague, Ms. Kasper.
So, okay, now let's talk about debugging. when you use an entity component system in a program, you will have a lot of entities very, very quickly. So for this, just printing all the values into just a console is not very feasible anymore. And for this reason, I wrote for my bachelor thesis a debug console using C++, JSON, and a TCP connection to get some good insight into the data used in the program. To connect to the console, if the entity component system, in this case the Vienna Entity Component System, is compiled in debug mode, it will automatically try to connect to the console. Both the console and the entity component system have a default port specified, and if not other specified, the connection will be automatically. But if you wanted, you could also define another port in the same network to, for example, have the application running on the gaming PC or similar, and to debug from a laptop in the same network. Once you are connected, so either you can load a saved snapshot from file, or you can make a new snapshot from your system. A snapshot will generate a table of all current active entities and their components. It's possible to filter through the archetypes, entities, component type, and tags. And like this, you can have a real insight in what's happening in your system. If you find an entity that you're interested in, you can add it to the watch list and see the changes in the status in the live view later. And when you have a snapshot, you could also save it to file, which will generate a JSON file with a snapshot in the file name, with the timestamp in the file name, to compare it to other snapshots later. Here we see an example of what a typical snapshot could look like. We see it's ordered by archetype and then by the entity index, and contains all the data of your current system. It's possible to filter over here, get a new one, or save it to file. And on the bottom, we also have some statistics for the snapshot, like, for example, how many entities are the total, how many components, and what's the parse time of the snapshot to see if that is really a current one. Once you have a snapshot and added some to the watch list, some entities, you can also open the live view, which will display a graph showing the number of entities that are currently in the system. It will show the development of the entities over time, and the graph always resizes to the visible range, so that if we get suddenly a lot of entities in, you will be able to see that. But also when the amount of entities shrinks again, that you will be able to see the small differences in the numbers. Under the graph, a watch list will be displayed with the entities marked by status. If the entity is all white, then there's no changes to the watch list. If it's yellow, then one or more component value has changed, and the changed value will be the one displayed. And if it's red, the entity is deleted and not currently active in the system at all. It's possible to open the watch list next to the live view to see the differences in the values. Under the graph, there's also some statistics of the current number of entities, the average number of components per entity, and the estimated memory usage of the entities that are currently active. This is a picture of what a live view would look like. We can see in this test case, we had a rapid increase of entities and then a sudden drop, which is here visualized. Currently, there are 24 entities active with an average of 3.21 components, and the whole entities use about 400 something bytes. And from the watch list, one of the entities I had in the watch list is already deleted, so it's marked. And if we still have enough time, we could also show the video. So this video demonstrates how to connect to a current running system. And here we get a new snapshot, which, since there are not many entities currently in the system, the snapshot took very, very, very little time. Possible to filter for specific entities and add them to the watch list. Yeah. So we add some to the watch list to look at them in the live view and later. Here is the live view started. First, it's possible to resize, and then if we start the live view, one of the entities that I marked as for the watch list is already deleted, so it's marked red. The test case that I have is adding entities per second, so we can see how the value changes. In my test program, it's also possible to add a lot of entities, which I'm showing here. So we add about now 300,000 entities into the system, which is about 3.22 megabytes in size. And it's also possible to have the windows next to each other, get some good insights, and also new snapshots while the live view is running. And this is a good way to be able to debug the system when there's also a lot of entities present. It's also possible to update the watch list while the live view is running. Also to, in theory, delete entities from the watch list again to get some good insights into the program. And with this, I will conclude my talk and give the mic back to Professor Hlavacs.
So thank you very much. So we'll continue with our presentation. And we'll conclude our presentations. We have seen that ECS are actually is a useful architectural pattern. It's widely used in the games industry. Unity uses it. Many games use it. You have a lot of architectural choices which directly influence the performance that you have. So you have to highly optimize it, and a lot of these entity component systems, you see they're highly optimized. There's lots of code just for optimization. Parallelization is difficult, but it's actually feasible. You can do it, but it's very delicate, let's put it that way. And debugging is hard, so you need useful tools, and I think we've shown very, very useful debug console that actually gives you insights into the entity component system. We have also seen that it's actually feasible to let an LLM create it for you if you're content with what comes out of that. We've seen a lot of possible optimizations coming up. You can use these archetype graphs, you can use bit sets, you can use like a view cache that speeds up the creation of views, and so on. So let's see what the future brings. And with this, I will conclude my talk. Thank you very much.
Thank you for your talk. Great insights.
Thank you.
And with that, we'll next talk. Okay.